what I was going to cover today, and then I thought, wait a minute, is that going to be completely wrong? And I wrote some things out like, yep, I was about to do something completely wrong. And so then I took some time between my previous class and this one to fix it. So everything's fine now. Okay, I'm not sure how long it's going to take. I'll just, or where I'm supposed to end. We'll just, I know my direction, and that's about it. So, and we'll see how this goes. Okay. Now, all right. So where we're at, pick up where we left off, is that for the simpler system of ODEs, y prime is equal to AY. We know the solution there. That is the exponential, matrix exponential, EVAT, times the vector of initial values y of 0. Okay. And then, let's see. So from there, is that now we want to consider system of ODEs where we've added some source term, v of t, and how we handle that. And actually, that was handled completely, I believe, in the case of A being diagonalizable. And I'm trying to remember how fairly I addressed the case of A being non-diagonalizable, but okay. So might be thrown off my path a little bit here. Because I certainly can write down what the solution formula is. Now, I'll go ahead and write it down. Y of t. So we have the same first term. And then to account for the source term, we have its integral. Okay, and I'd actually fully derived this formula in the case of a scalar ODE. So in other words, the matrix A is 1 by 1. The solution Y is just a number, not a vector. Okay, so I wonder if I have to put off what I plan to cover today. Sorry, I'm like having a pedagogical crisis here. Okay. I know. All right. So, right. And actually, the second homework, I had you verify this formula, but in the scalar case, right? Yeah, computing a derivative with respect to t and using a fundamental theorem of calculus and.
Yeah, I think that's the one I'm okay on.
Yeah. So.
Yeah. Yep.
Okay. Now. As far as A is not necessarily diagonalizable. All right, so, and after that, cover all the bases, we have A expressed in terms of its Jordan form. And as I've shown you before, we have this new system of ODEs. W prime is equal to JW plus C of T, where W is X inverse Y, and C is equal to X inverse B. So same kind of system, just J is a much simpler matrix because it's block diagonal. And it had been worked out in the case where J is diagonal, that the system of ODE separates completely, and then we knew how to solve all of those and built up a solution from there. In the case where this term, this C of T, wasn't here, then that part was also worked out. Now, the thing is, if I write it this way, W prime minus JW is equal to C of T, and then I multiply both sides by e to the minus JT. Okay. Then, proceeding is how it's done in ODE textbooks for single ODEs, not systems like this one. You can show that this is the derivative of e to the minus JT times W. And the easiest way to show that is, or like to prove that, is you represent e to the minus JT by its Taylor series. What?
No, sorry, it's not just like a product rule.
Yeah.
Yeah.
If you carry some product rule, you get this.
Yeah. Okay.
Yeah.
Gotcha.
Yeah. So you can take the derivative of this with respect to t by representing e to the minus JTs as Taylor series and show that this extra factor of j pops out. So then you can integrate both sides, and what that would give you is this formula right here for W of j. But then you undo a change of variables, and it all works with y, t, and a.
So you're writing all the e to the negative JTs as its Taylor series.
Yes.
And then in turns, you find W, T, you can change your variables and you're back to the.
Yeah.
Okay, cool.
Yeah. Actually, you know what? Even though it's not what I plan to cover today, I want to take time to show that. Because,
I'd like to see it.
Okay.
Cool.
All right. So, in particular, I want to. Well, okay. So if I take its derivative by product rule, what will we get? We get e to the minus JT W prime. Now, when it's matrices and vectors you're differentiating, product rule still applies, but you must preserve the order in which they're written. So I cannot reverse these.
Oh, because.
Matrix
Matrix
multiplication.
Yeah. Okay.
Yeah. Okay.
Okay.
And then I have plus the derivative of e to the minus JT times W. So what I have to, so all I got to do is show that this derivative is equal to minus j e to minus JT, and then that would be done.
Yeah.
Because everything else is in place. And this is something worth showing because I'm going to write this as a Taylor series, and this involves doing some manipulations on summations that you all should know, because or are valuable to know, because it happens sometimes as math teachers and so forth that having to rewrite summations in different forms to get some results, and how those manipulations should go. And I don't know if that's really taught, honestly, in a class. I mention it sometimes when it comes up in whatever class, but
right.
yeah. So I think this is a good thing for you all to see.
Okay.
All right. So now I'm going to focus just on this derivative. So what I have is Taylor series. So I have minus jt to the k power over k factorial prime. And now I want to take a derivative of that with respect to t. All right, so now anything that doesn't depend on t, I could just pull out a derivative, yeah. So the summation, and then we have minus j to the k over k factorial. And then I'll take a derivative of t to the k, but that's going to be kt to the k minus 1.
Gotcha.
Okay. But now I need to write this in a form where you can easily see that it's equal to minus j times the original exponential. And that's going to take some doing here. Now, one thing that'll help is I can actually write this way. All right, same expressions inside. And start it at k equals 1. So notice I've changed nothing except k equals 0, now starts at k equals 1. Can anyone tell me why, in this case anyway, it's perfectly valid for me to do that?
Factorial is 1. Yeah, doesn't that all just turn to 1?
Well, okay, that's identity. That's 1.
Right.
Okay,
Okay, yeah, sorry, identity. 1.
Okay, but what of the rest of it?
The rest of it is also 1. Or k, I guess. Right, t to the 1.
Okay, so.
Oh, wait, no, you're plugging in. We're taking out the 0, sorry, to the negative first.
Okay, but so the thing is, you're focusing on the term where k is 0.
Yeah. Oh, okay, 0. Yeah.
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 The first term is 0 anyway.
I was plugging in 1. And
Oh, okay.
Yeah.
Yeah.
Weird.
Yeah, so the first term of it's going to be 0, so I'm just going to not bother with it.
Okay.
Yeah, so the series will have the same value if I start k at 1.
Okay.
Now, next what I can do is, okay, shoot, I'm running out of room. I can negate some awful board practices here and go to where I have room. Okay. At least it'll look neater in your notes than it will on the board.
Good communication.
Okay. All right. Okay. All right. So first of all, I have k factorial to k over k factorial, but the last factor of k factorial is k. So those will cancel out. So now I can have a sum, k equals 1 to infinity, of minus j to the k over k minus 1 factorial t to the k minus 1.
Okay.
by simplifying B's.
Oh, okay, so
Yeah.
sorry, I just.
Yeah, because K factorial is product of everything up to K.
Right.
You can't solve that K with this K.
Yeah, okay.
So now I got a product of everything up to K minus 1. Yeah. But then what I can do is I can replace this K with a K minus 1 as long as I pull a minus J out.
Just taking that. What did you say?
I have minus J to the K. I can reduce that to K minus 1 as long as I take a minus J and pull it outside. And since I'm starting at K equals 1, I always do have at least one factor I can pull out.
Uh-huh. Yeah.
So now, notice I have K minus 1 everywhere. So I can rewrite the sum by think of it as replacing K by K plus 1 throughout. So it's like a change of variable in the sum. So if I replace K by K plus 1, then all the K minus 1s become Ks. But because I increased K throughout, to compensate, I have to start K 1 less.
Oh, yeah.
K equals 0 to infinity. So that's the main thing I'm wanting to see, this shifting of indices.
Okay, shit.
So
Okay.
so you shift up 1 inside, down 1 outside.
Right.
Yeah,
Okay.
or vice versa, depending on what you need to do. But this is the exponential. So this minus j e to the minus jt.
Oh, yeah, because that's, the polynomial expansion.
Yeah.
Okay.
Oh, wow. This is totally wrong over here. Doesn't affect any of the rest of us, magically. That should be a C. Whoops. Okay, carrying down from here. Yeesh. Okay. Questions about showing app? Putting from virtual land. Because now that that's established, you can go back to here. And if you were to, because now on the left side, you have a derivative of something. So if you integrate both sides, and I did this earlier, the scalar case, then this solution formula will pop out. Okay. And really, it's that solution formula that I want to work with, because there's still a disconnect between, like, okay, if I have a higher order ODE, like a second order, that rides a first order system, I can solve it that way. But you can't really see from this solution formula how you get to solution techniques presented like in ODE texts. And so what ODE students are learning about how to solve these. And so I want to bridge that gap. So you see, oh, that's where these things come from that they're teaching in those kind of classes. Okay. So for that, I actually need to use a different definition of a matrix exponential than what I've been using here. The whole time I've been using it, the definition as a Taylor series, just from a Taylor series for V exponential. But now I need to use the fact that it solves this kind of ODE. And in fact, what I've just shown here shows that two perspectives are equivalent. So I can use either definition as think of the exponential as a Taylor series, or think of the exponential as a solution of this system of ODEs.
So what you're saying is,
Well,
wait, what we just did.
Shows that those two perspectives are consistent with one another.
Right, so you wouldn't necessarily need the change of variable from this perspective.
This you mean?
Yeah.
Yeah, we're gonna move on from that. But I'm not sure what you're referring to.
I'm trying to bridge the gap myself. So you're saying this, because you just showed the differentiation of that one piece using the.
Okay.
Oh, sorry.
Okay.
Expansion. Taylor polynomial
Right.
expansion.
Yeah, and what I've shown is that the derivative of a matrix exponential.
Oh yeah, we were only dealing with that one.
Yeah. Okay. I'll write down what my point. I'll need to erase this up. Okay. So. There are many ways to define matrix functions. We're just dealing with these two. So. All right, so first definition I use was this Taylor series. Okay. The second definition that's going to be more helpful for what I'm about to do is that each so I'll define a matrix X of T is the matrix exponential if X has the following properties. X prime is equal to A times X. And that's what I just showed is true from a Taylor series perspective.
Okay.
And the other condition, X of 0 is the identity. So those two conditions together uniquely define a matrix exponential. And in fact, if I went back to the Taylor series definition, I plugged in T equals 0, I would get identity. So all terms would go away except for K equals 0, and you get identity over 0 factorial. So these two notions are equivalent. Okay. Now, oh, shoot, I didn't want to use that letter. Dang it. Okay. Sorry, need to change letters. Call it G. I think, well, a couple of you took Math 605. And I think Dr. Tim, I've talked about like a fundamental matrix. And I believe that's actually is another term for matrix exponential.
She probably did.
Okay.
It's been a long time.
All true, yes, it's been about a year, so. Okay, now, so the thing is, suppose I consider one column of the matrix exponential. So GT times the standard basis vector EJ. So refresh your memory. It's a column vector of all zeros with a 1 in the jth position, the jth column of identity. And I'm going to call this vector UJ, just for convenience. Okay. Oh, don't have a whole lot of time. Then here's what I can say. UJ is a solution to this system of ODEs, just because the whole matrix is a solution of the same ODE, system of ODEs. So any column of it also, actually, literally what I'm doing is I'm taking this system of ODEs and I'm multiplying both sides by EJ on the right. So this is a matrix equation. I'm taking one column of that matrix equation. And the initial condition is that. So same thing here, I'm taking a column of both sides of this matrix equation.
Yeah.
So what this means is each column of a matrix exponential is a solution of this system of ODEs satisfying certain specialized initial conditions, where all the initial values are 0 except one of them is 1. So, but the thing is, when we're solving ODEs, like system of ODEs that come from higher order ODEs, okay, we're trying to find all the solutions of this system of ODEs, but we don't really have control over can't conveniently specify what initial conditions they satisfy. So here we have if this A is an n by n matrix, we have n particular solutions of a system of ODEs. But what if we have instead just arbitrary solutions of this ODE that were found like by some other method? So I can say I need to find a matrix X of T, this is what I want to use X for, be a matrix consisting of n columns. Okay. And let's suppose that each column is a solution of this system of ODEs. So then I can say the following. X prime of T is equal to A X of T. So in other words, this matrix of solutions satisfies the first condition for being a matrix exponential. But I don't know about this one. So the thing is, if I plug in T equals 0 in here, well, who knows what I'll get? I can get anything. All right. So, but the thing is, each one of these columns is a solution to this linear ODE. Therefore, if I take any linear combination of these solutions, it's also a solution. So, so if I multiply both sides of this matrix equation by some arbitrary matrix B, and so B is any matrix that has n rows. So, and in fact, I can write it this way. I can move with B inside the prime. Yeah, I'm assuming B is a constant matrix, independent of T. So any linear combination of solutions is also a solution. That's what we have here. So each column of this is a linear combination of these solutions, therefore it's also a solution. And we can see that by multiplying both sides and see, oh, this prime is equal to A times the same thing. All right. So now I'm going to choose a particular B. Let B equal the inverse of x of 0, if assuming it exists. So what that would mean is these solutions have to be linearly independent. Okay. So then x of t times b, if I plug in t equals 0, it's identity. So now I have a matrix that satisfies the second condition for a matrix exponential. So that tells me that x of t, x of 0 inverse is g of t. It is a matrix exponential. So now I have yet another way of describing a matrix exponential. I don't need to restrict myself to solutions of a system of ODE that satisfies certain initial conditions. I can take any n linearly independent solutions, no matter what initial conditions they satisfy, as long as I multiply by the inverse of those initial values, and then I can describe a matrix exponential this way. So following these two definitions, and I now have my third one. E to the AT is x of t, x of 0 inverse, where x of t consists of, as columns, n linearly independent solutions. So these are solutions of xj prime equals ax with axj. So it doesn't matter what initial conditions values they satisfy, because of this, to like normalize them, if you will, I got the matrix exponential. And so it can satisfy both these conditions. It's possible that may have popped up in 605. I know somewhere in the book where Dr. Chen covered it, it's never matter. Okay. Well, I'd be interesting to walk down memory lane and look in your notes or something and see if it's there.
Yeah. We didn't cover too much.
Okay. All right. My actual goal for today was to use this notion of the matrix exponential in this solution formula to show how to derive methods for solving inhomogeneous ODEs that pop up in ODE classes. But I can do that Thursday.
Okay.
So there's nothing, well, it's almost time to stop anyway. So I can take a few minutes for any questions anyone has about this or homework. Make sure I got pictures from a board. Okay, so I did all that. Okay, so I need a picture of this board. I've been slowly but surely catching up on transcribing notes. I did one from a couple classes in September, but I need to do a couple more now. So homework questions of any kind?
I'm just, yeah, I think I told you earlier, doing some little algebra wrong somewhere, but I'm sure I can figure it out.
Okay. Mm-hmm. Okay. Any questions from down the coast? Definitely send any homework questions my way by email if you need to. So. Okay. Thanks for letting me know, Taylor. Okay. Okay. Well, I would say let's call it a day, but I'll see you all in a half hour.
Oh, yeah.
Talk about Chebyshev polynomials. So. Okay. Well, see you then.
Thank you.
Yep.
Yeah.
Thank you.